In this video, I am going to discuss limiting molar conductivity, Kohlrausch law of independent migration, degree of dissociation and dissociation constant, and problems based on it. In the previous video of electrochemistry, we have learnt lambda m is equal to volume multiplied by kappa. According to the equation, molar conductivity is directly proportional to volume that contain 1 mole of electrolyte. On dilution, molar conductivity increases as the volume of solution increases that contain 1 mole of electrolyte. If we further keep on diluting the solution, molar conductivity reaches to its maximum value at infinite dilution, or you can say at zero concentration. At that time, molar conductivity is called as limiting molar conductivity and it is denoted by lambda naught. First of all, we are going to discuss limiting molar conductivity for strong electrolyte. Strong electrolyte dissociates completely. For strong electrolyte, relation between molar conductivity and limiting molar conductivity is as follows. Lambda m is equal to lambda m naught minus a root c, where a is a constant for a given solution at given temperature. That means it is temperature dependent quantity. And C is the concentration expressed in moles per liter. When you rearrange this equation, you will get lambda m is equal to minus a root c plus lambda m naught. When you compare this equation with a straight line equation, y is equal to mx plus c. Here lambda m can be compared with the y, so we can plot lambda m on y-axis and x can be compared with root c. So we will plot root c on x-axis. As concentration increases on this direction, dilution will increase on the opposite direction. If we keep on increasing the dilution, it reaches to infinite value. And at the time of infinite dilution, concentration will become 0. For certain value of concentration, you will get molar conductivity of a strong electrolyte at this point. But when you increase the dilution, you will get higher value for lambda m. As it follows a straight line equation, when you connect both the points, you will get a straight line which intersect at y-axis. And this intercept will be equal to lambda naught. This is the limiting molar conductivity. So for a strong electrolyte, if we just extrapolate this line, you will get molar conductivity at infinite dilution or limiting molar conductivity. Now let's examine limiting molar conductivity for weak electrolyte. Weak electrolytes do not dissociate completely. On dilution, dissociation of weak electrolyte increases. Consequently, the number of ions in total volume of solution that contain 1 mole of electrolyte increases. That's why molar conductivity keeps on increasing on dilution. If you plot molar conductivity of weak electrolyte at different concentration, you will get this kind of pattern. And when you connect all the dots, you will get this line. That means it doesn't follow this equation or the straight line equation. So how do we measure limiting molar conductivity for weak electrolyte as we did for strong electrolyte by just extrapolating the straight line? As the solution of this problem, Kohlrausch presents a law named as Kohlrausch law of independent migration. This law states that limiting molar conductivity of an electrolyte can be represented as the sum of individual contribution of anion and cation of that electrolyte. That means limiting molar conductivity of an electrolyte is the sum of limiting molar conductivity of cation and limiting molar conductivity of anion. For example, limiting molar conductivity of NaCl is the sum of limiting molar conductivity of Na plus ion and limiting molar conductivity of Cl negative ion. Or in other words, individual ion contributes to the limiting molar conductivity of that electrolyte. Each ion has its specific value for limiting molar conductivity, irrespective of its counter ion. For example, this is the limiting molar conductivity for NaCl. It is the sum of limiting molar conductivity of Na plus ion and limiting molar conductivity of Cl minus ion. And this is the limiting molar conductivity of KCl. It is the sum of limiting molar conductivity of K plus ion and limiting molar conductivity of Cl negative ion. In both the equation, Cl negative ion is the common one. Limiting molar conductivity of Cl negative ion is 76.3 Simon centimeter square per mole will remain same for KCl as well as for NaCl, irrespective of their counter ion. In KCl, counter ion of Cl negative ion is K plus, while in NaCl, counter ion is Na plus. But irrespective of their counter ion, limiting molar conductivity of Cl will be same for both the electrolytes. Now let's solve one problem based on Kohlrausch law. Limiting molar conductivity for NaCl, HCl, sodium acetate are 126.4, 425.9 and 91 Simon centimeter square per mole respectively. Calculate the limiting molar conductivity for acetic acid. First of all, write the equation for limiting molar conductivity for all the electrolytes given in the question. Based on Kohlrausch law of independent migration, limiting molar conductivity for NaCl is the sum of limiting molar conductivity of Na plus ion plus limiting molar conductivity of Cl negative ion. And it is given 126.4 Simon centimeter square per mole. Now write the equation for HCl. So here you will get limiting molar conductivity for HCl will be equal to limiting molar conductivity of H plus ion plus limiting molar conductivity of Cl negative ion. And it is equal to 425.9 Simon centimeter square per mole. Now write the limiting molar conductivity of sodium acetate. It is equal to limiting molar conductivity of acetate ion plus limiting molar conductivity of Na plus ion. And it is equal to 91 Simon centimeter square per mole. Now write down the desired equation for limiting molar conductivity of acetic acid. It is equal to limiting molar conductivity of acetate ion plus limiting molar conductivity of H plus ion that we have to calculate. Now label the equation. So we can label this equation 1, equation 2 and this is equation 3. And this is the desired equation. Now match the ions with the desired equation and the given equations. Limiting molar conductivity of acetate ion is given in equation 3. Limiting molar conductivity of H plus ion is given in equation 2. Then, to get the values of these ions, we have to add equation 2 and equation 3. So let's add equation 2 and equation 3. When you add equation 2 and equation 3, you will get limiting molar conductivity of acetate ion plus limiting molar conductivity of H plus ion plus limiting molar conductivity of Na plus ion plus limiting molar conductivity of Cl negative ion. Now you have to add these values also. Now label this equation as equation 4. Now mark the values that we don't want in our desired equation. So here, limiting molar conductivity of Na plus and Cl negative we don't want in our desired equation. And these values are also given in equation 1. So we have to subtract equation 1 from equation 4. So let's subtract it. When you subtract it, these values will be cancelled out. And you will get limiting molar conductivity of acetate ion plus limiting molar conductivity of H plus ion is equal to. Now subtract the value 126.4 from this value. On calculating, you will get 390.5 Simon centimeter square per mole. And according to Kohlrausch law of independent migration, sum of these ions will be equal to limiting molar conductivity of acetic acid. So the answer of our question is 390.5 Simon centimeter square per mole. Now come to the another application of limiting molar conductivity. For a weak electrolyte, ratio of molar conductivity and limiting molar conductivity is equal to its degree of dissociation, that is denoted by alpha. So mathematically you can write alpha is equal to lambda m over lambda m naught. For example, AB is a weak electrolyte. It partly dissociates into A plus ion and B negative ion. So initially there is 1 mole of AB and 0 moles of A plus and B negative ion. At the time of dilution, alpha moles of AB get dissociate into alpha moles of A plus ion and alpha moles of B negative ion. So there will be 1 minus alpha moles of AB will remain. When you divide the number of moles by volume, you will get concentration. So the concentration of AB will be equal to 1 minus alpha over V, and the concentration of A plus ion will be alpha over V, and it is also equal to concentration of B negative ion alpha over V. Now when you calculate the dissociation constant K for AB electrolyte, you will get concentration of A plus ion multiplied by concentration of B negative ion divided by concentration of AB. Now place the value of concentration in this formula. Concentration of A plus ion is alpha over V, and the concentration of B negative ion is alpha over V divided by 1 minus alpha over V. It is the concentration of AB electrolyte. Now solve this equation. So here you will get alpha over V whole square divided by 1 minus alpha over V. When you simplify this equation, you will get alpha square multiplied by V divided by 1 minus alpha into V square. So this volume and one of the volume from the denominator will get cancelled out, and you will get alpha square divided by 1 minus alpha multiplied by V. 1 over volume is also equal to concentration. So we can replace 1 over volume with a concentration. So you will get another form of this equation, alpha square C over 1 minus alpha. We just have learned alpha is equal to lambda m over lambda m naught. So when you place the value of alpha in this formula, you will get lambda m over lambda m naught whole square multiplied by C divided by 1 minus lambda m over lambda m naught. When you solve this equation, you will get lambda m square multiplied by concentration divided by lambda m naught square multiplied by lambda m naught minus lambda m divided by lambda m naught. So this lambda m naught will get cancelled out with one of the lambda m naught present outside. And here you will get lambda m square C divided by lambda m naught multiplied by lambda m naught minus lambda m. So this is the formula for the calculation of dissociation constant. Now let's try to solve one question. The molar conductivity of 0.025 mole per liter methanoic acid is 46.1 Simon centimeter square per mole. Calculate its degree of dissociation and dissociation constant. Given limiting molar conductivity of H plus ion is equal to 349.6 Simon centimeter square per mole, and limiting molar conductivity of HCOO negative ion is equal to 54.6 Simon centimeter square per mole. Here we have to calculate degree of dissociation. It is equal to lambda m over lambda m naught. Lambda m of methanoic acid is given 46.1 Simon centimeter square per mole. And the value of limiting molar conductivity of H plus ion and HCOO negative ion is also given. So by using Kohlrausch law, we can calculate the limiting molar conductivity of methanoic acid. First of all, write the equation for limiting molar conductivity of methanoic acid. So here you will get limiting molar conductivity of methanoic acid is equal to limiting molar conductivity of HCOO negative ion plus limiting molar conductivity of H plus ion. When you place the values in it, you will get limiting molar conductivity of methanoic acid is equal to 54.6 plus 349.6. When you add these values, you will get limiting molar conductivity of methanoic acid is equal to 404.2 Simon centimeter square per mole. Now use this formula to calculate the degree of dissociation. So here you will get alpha is equal to lambda m over lambda m naught. When you place the values in it, you will get value of lambda m is given 46.1 Simon centimeter square per mole. And we just have calculated the value of limiting molar conductivity lambda m naught. So here we have the values 46.1 divided by 404.2. For the ease of calculation, convert these values in scientific notation. So here you will get 4.61 into 10 divided by 4.04 into 10 raised to 2. So 10 will get cancelled out with 10, and when you solve it you will get approximately 1.1 over 10. When you solve it you will get 0.11. So alpha is equal to 0.11. For the dissociation constant we have formula K is equal to alpha square C over 1 minus alpha. Now place the value of alpha in this equation. When you place the value of alpha in this equation, you will get 0.11 whole square. Multiply by 0.025 mole per liter, that is the value of concentration given in the question, divided by 1 minus 0.11. When you solve it, you will get 0.0121 multiplied by 0.025 mole per liter divided by 0.89. For the ease of calculation, let's convert all the values in scientific notation. So here you will get 1.2 into 10 raised to minus 2 multiplied by 2.5 into 10 raised to minus 2 divided by 9 into 10 raised to minus 1. So when you solve it, you will get 3 into 10 raised to minus 4 divided by 9 into 10 raised to minus 1. So 3 ones are 3, 3 threes are 9. Now when you solve it, you will get 0.3 into 10 raised to minus 3. Now shift the decimal point to the right side. So here you will get 3 into 10 raised to minus 4 mole per liter. It is the value of dissociation constant. So here we have calculated degree of dissociation and dissociation constant.